English easy.
Hi, so I want to talk about a really interesting problem from the GATE 2017 exam, namely question number 39. And this is quite a hard problem, so much so that the official key solution was incorrect. So I might as well set the record straight on this. So what is the setup? So we have two alphabets right here, A and B. You can just think of them as just a finite set. Actually, they don't necessarily need to be a finite set, but let's just assume that they are a finite set here. Then we have some pound symbol right here. It's just like a separate symbol that's not in the alphabets. Okay, so we got two alphabets here and some symbol that is not in either one of them. And we have a function f that goes from strings over A to strings over B. So this is just from taking strings from one alphabet to another alphabet, and it can be a completely arbitrary function. The only thing that we know about it for sure is that it's a total function. And if you don't know what a total function is, it means that no matter what the input is to the function f, the output is defined. So no matter what string over A star that I give, f of whatever that string is some string in B star. So it's not necessarily unique, but there is a string in B star. That's just what it means to be total. Okay, so we're going to define a language here called L sub f. So the f here is defining what the language is, and the language is over all strings over A star. So look at every single string in A star. Then I'm going to form this string, which is basically just take the string that you got, put a pound sign in the middle, just a delimiter, and put the f function result on that x. So remember, x is in A star. So that means f of x, which is in A star, is defined. So this string is of the form some string in A star, followed by a pound sign, followed by some string in B star. And the thing on the right side could be totally arbitrary because the function, other than being total, is completely arbitrary. Okay, so that's what the L sub f language is. So the question is, I'm not going to put the answers here. I want to actually arrive at the answer here. Is what is the relationship between f and L sub f? So note that f is a function and L sub f is a language. So it's not like we can directly compare them, but we want to know if f has some properties that are useful, what can we determine about L sub f? And if we know some things about L sub f, what does that in turn imply about f? So let's get started on this. Okay, so I want to address the scenario of where f is computable, then what can we determine about the L sub f language? Okay, so we can talk about other properties that f might have, but f being computable is obviously an important characteristic of a function. If it's not computable, we can't really evaluate it, right? So let's assume that f is computable. So that means that if I am given some input x, I can compute f of x. That's what I can compute. So what can we determine about L sub f? So L sub f, remember, is this language. So it's the language of x followed by a pound sign followed by f of x, where x can be any string in A star. So the thing here is we're asking something about a language. So we want to figure out whether it's like decidable, recognizable, or whatever. So let's just say that we wanted to figure out it was decidable, just as an example. Then that means that we got to produce an algorithm for this thing. And even if it was recognizable, we would have to produce some procedure where we're given some input and then answer accept or reject, as the case may be. So here we're given some input that looks like this. So actually it's not necessarily that, but we'll get to that. So then we're given something followed by a pound sign followed by something, and we want to verify whether the thing on the left, when f applied to it, is the thing on the right. But the thing is, it may not be given in this specific format. It may be some arbitrary string, because L sub f, it's got to answer questions about any arbitrary input. It might run forever if we're making a recognizer, but it's got to answer questions on all inputs. So let's see what we can do with this. So let's say that we are given some input w. Well, notice that this language is only strings of the form some string followed by a pound sign followed by something in B star. Okay, so it's something in A star followed by pound sign followed by something in B star. If it's not of that form, it cannot be an else of F, so we can just reject it immediately. So the first step is to reject if this string W is not of the form A pound sign B, where A is in A star, B is in B star. Okay, so if it's not of that form, forget it. But then now after this point, we know we must have a string of this form. And clearly this is something that we can check because these are finite alphabets. Okay, so this is a finite alphabet. Well, I can just figure out whether this thing is an A star just by looking at each of the characters and comparing against the alphabet. The pound sign is pretty obvious to check, and then B is the same thing. It's just checking whether all the characters are in that alphabet. In fact, you can even make a regex for it, but that's beside the point. Okay, so then now what we want to do is we want to, at this point right there, verify if F applied to A, which is the thing on the left side here, is equal to B. Okay, well, the thing is, F is computable, right? Because that's the assumption that we're making here. So if F is computable, then I can compute what F of A actually is. So let's do that. So the second step is, let's compute F of A. Need a better A there. And so this step must take a finite amount of time because it's a computable function. It must take a finite amount of time. So then, since this is computable, that means that we have F of A written somewhere, and we have B written on the tape right here because we just verified whether the input is this. So all that we need to do is just to match these two strings and see if they're actually the same. So then all we need to do for step 3 is accept if and only if F of A is equal to B. Okay? And that is very easy to do because that's just a finite length string comparison. So this takes a finite amount of time because it's just checking the input against finite alphabets, and you can even make a regex for it. This takes a finite amount of time because by assumption the function f is computable, and this one takes a finite amount of time because it's just a finite length string comparison. So what is the runtime of this thing? Well, it's finite in total. And we are going to accept or reject as the case may be, depending on whether the input is in else of f. So in a finite amount of time, we are accepting the input or rejecting the input correctly, which means we just made a decider for the language, and therefore the language is decidable. So then what we can claim here is that if f is computable, that implies that L sub f is decidable. And on the actual test, they use the word recursive, but it means exactly the same thing. It's just a different term for the same thing. All right, so then now let's do a different style approach where we assume something about L sub f, and then we want to prove properties about f. So let's get going into that. All right, so let's make an assumption about L sub f. We figured out that it was decidable if f was computable. Maybe we get the converse too. So let's assume that L sub f is decidable for now, and then let's try to figure out what f is, whether it's computable or not. Let's think about what L sub f decidable means. So L sub f means that there is a decider, let's call it M sub f for this language, L sub f. So that means that M sub f on some input x, this is going to accept if and only if x is in L sub f, and rejects if and only if it is not in there in a finite amount of time. In fact, this is all that you need to actually do that, but it runs in a finite amount of time, this M sub f thing. So let's recall what L sub f is. So L sub f is something that looks like x pound sign f of x, and where x is just some arbitrary string in A star. So here, given a string of this form, then this machine supposedly will figure out whether or not it's actually in here. So if we have a string, it can figure out whether it's of this form, whether it's some string followed by the f thing for it. So then how do we actually figure out anything about the function itself? So here we know that we want to figure out something about the function f specifically. So let's try to see what we can do about this. So this function f is going to take some input x, and then what we want to do is we want to produce the correct value of f of x. The problem is that this input x here, we don't know what this input is over this part of it, the input for the m sub f machine actually is. So I know that I have the input x right here because the f by assumption is getting this input, it's just a function, and it wants to produce the correct value, which is this associated value right here that's stored somehow in the L sub f language. But we want to actually extract that out. But I don't know what that actually is. But here's the key. We know that f is total. So remember, f is a total function, which means that no matter what input you got, you always have a defined output. So no matter what input this function f gets, that means that there is something in here of the form x pound sign something where it's in L sub f. It's not like it's not defined. It is in there for sure. So what we need to do is to search for it. But I have no idea what that f of x actually is. It's some string, but I have no clue at all what it is. So let's figure out what we can do. Well, let's just run. So first step, run all strings in B star. So remember the f of x is going to be some string in B star in any order, one at a time. So I'm going to call those strings y. So y is the second half of the input. Well, what we can do is to send it off to the m sub f machine and let it figure out whether or not it's in there. So if it is in there, that means that we just found a string of the form x pound sign y, and so therefore we should accept. Okay, so step A inside here is run m sub f on input x pound sign y, and then if m sub f accepts, output y. So remember that f is a function. It's not like a recognizer or anything, so it has to actually output something. So the thing that we want to output is the corresponding value for x as dictated up here. So I guarantee that this runs in a finite amount of time, even though it seems like we're trying everything here. But we know that f is total, which means that one string y, in fact exactly one string y, is going to have m sub f accept right here, which means that we will output it. As long as there's at least one, but in fact there's exactly one in this case because f is total. All right, but it turns out that we can even do better than this. So what if I told you that we can actually relax the condition a little bit? So instead of just being decidable, let's let it be recognizable, which means that if the input string is not in the language, the machine for it may run forever. If it is in there, it will stop eventually. But if the input is not in there, then the machine may run forever. So we don't have a decider anymore. We have a recognizer. And so the rejects thing may not actually happen. In fact, the machine may never reject whatsoever. It might, but it has to accept correctly in a finite amount of time. The rejects one may never happen whatsoever. And by the way, another term for recognizable is recursively enumerable. That's just another term for the exact same thing. So how can we actually fix it down here to show that f is also computable in this case? What we need to do is add one thing right here, which is in parallel. And if you've never seen in parallel before, I don't mean literally all at once, because that means we have to check infinitely many strings at the exact same time, which is obviously impossible. What you do is you run the first string for one step, then you run the first two strings for 2 steps, then the first 3 strings for 3 steps, first 4 strings for 4 steps, and just keep going up. By the same logic we had before, there's exactly one string y that we're going to eventually find. So let's say it's the ith string, and let's say that it requires j steps to run. Then if I is smaller than j, that's a great English sentence. If I is smaller than j, then that means that this string y requires more running time than the first time we've ever seen it. But that's okay, because we're repeatedly checking the first I strings multiple times after that until something is accepted. If it was the other way around, then the first time we find y, it turns out we will accept the very first time. So at some point, this y actually exists. So therefore, this m sub f thing will accept at some point. It might take even longer than the original one because we're retesting strings, but we're only testing them for a limited duration. So I'm increasing that duration over time. So eventually, I'm going to run for long enough. So it might be a lot slower than the original way, but it still is a computable function. It always halts in a finite amount of time and outputs the string, which is really nice. So the behavior we can see now is that if this language is recursively enumerable, in fact, I'm just going to say recognizable, then that implies that f is computable. So what we can piece together from this is that if L sub f is recognizable, that implies that f is computable. And if we have the other way around, f is computable, then that implies that the language L sub f is decidable. Okay, so it's kind of an asymmetry here. It's not like an if and only if. It's close to an if and only if, but it's not quite there. And what we did was we exploited the various properties of the function being total and the L sub f having a finite alphabet, A and B, and we looked at the properties of decidable and recognizable languages and computable functions, and we were able to show that this is true. Cool. So if you have any questions about decidable or recognizable or computable functions, put them into the comments down below. As always, please like the video and subscribe to the channel. It really helps us out. There are many other links in the video description if you want to support the channel further. And as always, thanks for watching, and I'll see you next time.
That was easy. That was easy. That was easy.